S-block elements. Like I told you, we divide this periodic table into groups. Okay? Like a periodic table into blocks. Where, depending on where the last electron fills. That if the last electron occupies the s orbital, okay, then you become an s block element. If the last electron occupies the d block, the d orbital, then you become a d block element. And if the last electron occupies the p, then you become a p block element. And then if the last orbital occupies the f, okay, then you become an f block elements, and those are the actinides and lanthanides. So basically that's how we divide this periodic table. And so today we are going to talk about the s block elements, and these ones, they do include the group 1 elements, okay, the group 1 and the group 2. So we are going to see the chemistry of these elements. And under group 1 we have there lithium, then followed by sodium, followed by potassium, then cesium, rubidium. Then with group 2 you have there beryllium, magnesium, calcium, and so on, strontium, and so on. So that's the chemistry we are going to see. Okay, we are going to see how these elements, how their melting points are going to vary, the compounds they form, how their reactions, how do they react with different elements, different compounds, and so on and so on. And so if you can know that, then you'll be good as far as s block elements are concerned. So now the elements in s block have their valence electrons placed in the s orbital, like how I said. So if you are writing your electron configuration, maybe you write your 1s2. So as long as you have your electron in the s, whether you have 1, whether you have 2, then you are an s block element. Or you can be 2s2, okay, as whether 2s1 or 2s2, as long as you have your electrons, the last electrons, the outermost electrons occupying the s orbital, then we classify you as an s block element. So examples we have the alkali, those are the group 1 metals, and this is their outermost configuration. For example, you can start with lithium. Lithium is going to be 1s1, okay. If it is sodium, sodium is going to be 2s, yes, 2s2. Sorry, this is a mistake. So this is lithium, this is sodium. And then you go to potassium. Potassium is 4s1, and so on. So to summarize this, then we write this n, where this n is the principal quantum number. Then with group 2, or you can call them the alkaline earth metals, they have this as their outermost configuration. So where it can be 2s2, okay, it can be 3s2, it can be 4s2 for calcium, and so on and so on. Okay, so because the outermost electron occupies, so can you first take some water, occupies the s orbital, then it falls under the s block elements. So we can look at their different physical properties, okay, and if you can explain all these, then you are good. If you can explain how ionization energy is going to vary among these group 1 elements down the group, and to be sincere, you can see it is decreasing, okay, it decreases down the group. So this data supports that ionization energy decreases down the group. Now for group 2 elements, you can have a look. So this is the second ionization energy for group 2 elements, it's down. The second ionization energy, you can also see, okay, it also decreases down the group. But I want you to notice this, the difference in the second and the first ionization energies. So the difference is so high, which implies, and you're also going to compare the second. Let me bring the table. So you can compare, okay, the difference in second and first ionization energies for group 2 and the difference in second, okay, and first ionization energies in group 1. So basing on this, you can easily see, if you take the ratio by getting this, divide it by, you divide 73 by 520. The ratio you get, the value you get, is much higher than the value you get here, which implies that this electron, the second electron that was drawn, it was drawn from the same energy level. So the energy is almost the same. Not the same, but similar as compared to this. And how we can compare the atomic radii, okay? And you can see that down the group, the atomic radius is going to increase, okay? Down the group, the atomic radius is going to increase. The radii are increasing. This is higher than this, higher than this, higher than that. But if we are also going to compare group 2 and group 1, you see that group 1 elements have relatively high atomic radius than group 2. I hope you can see that. And so on, and so on, and so on for all the metals. If you had to compare barium and cesium, okay, cesium has a relatively large size, which is 0.2226, than barium. Okay, so this one supports the data. And you can compare melting point density, hydration energies. You should be in position to explain all this data, whether given data or whether you are just, it's a question just says explain how this, you should be in position to explain. Okay, so that's basically, that's why I told you that the periodic properties, they should be at hand, they should be part of it. Let's see how these factors, how these properties, physical properties, are going to vary among these elements. And if we start with melting points, we are going to see that group 2 elements have relatively higher melting point than the group 1 elements. Now if you remember bonding, yes, we studied bonding, okay? If you remember bonding and how a metallic bond is formed, then you should be in position to answer this question. Why do group 2 elements have a higher melting point than group 1 elements? Okay? It depends on the strength of the bond that is formed among the metal atoms. And so the bond in this case is a metallic bond, okay, which is formed by the interaction between the delocalized electrons, okay, and the positive metal ions that are formed by these metals. Now for group 2 elements, these ones, they do contribute 2 electrons, whereas group 1 elements, they do contribute 1 electron. And so when you lose 2, you form, let's say, let me say it is M, okay, with a 2 plus, whereas here you form N with just a plus. Now if you had to compare the charge density here and the charge density here, the charge density on this M ion is so high, and also the number of delocalized electrons is so high. So the force of attraction between the electrons and the positively charged ions is going to be high compared to group 1 elements. And so you need relatively much high energy to break the metallic bond, which is as simple as that. Not so? Yes. So basically that's what I've talked about. To repeat, the metallic radius of group 2 elements is smaller than those of group 1, than those for group 1. There should be 1 here. Sorry for that. Than those of group 1, making the metallic bond to be stronger. And I think I've tried to explain how the metallic bond is stronger, that having a small ionic radius, okay, with a high charge, a charge of +2 and a charge of +1, then the charge density is going to be high, okay? And if the charge density is high, then the force of attraction between the delocalized electrons, which are negatively charged, and the positively charged metal ions is going to be high. So the energy required is going to be much, leading to a high melting point. So let's see how density is. Now, the alkali metals are less dense due to a large atomic size. Remember, density is mass over volume. Okay? Now, it is a measure of how many particles, okay, that can occupy a given space. And basing on group 1 elements having a large size, okay, compared to group 2 elements, a given space may be a given volume of 1 centimeters cubed. If we are to compare the particles that can occupy this space, okay, for group 1 being large, the particles won't be as many as for group 2. So therefore the mass, if you are to compare the mass, okay, of these particles that are occupied by group 2, okay, and the mass of particles occupied by the group 1, you find that the group 2 elements, they will relatively be highly packed. There will be many, so the mass is going to be high. So as a result, if you consider their densities, then group 2 elements will have a relatively higher density compared to the group 1 elements. Okay? And basing on the force of attraction on the metallic bond, the group 2 elements, they will be closely packed, okay, in a given volume, in a given space. And so being closely packed, it means they will have a relatively higher density than the counterparts, the ferro counterparts. Now if you are to compare the oxidation state, this one is a net charge, okay? It is a net charge that is created on an atom when other atoms bonded to it are removed, okay, and then are removed as with a noble gas configuration. So in simple terms, for you to form a stable ion, you either gain or you lose. But metal atoms, they do form ions by losing, so that they form that noble gas configuration, okay? If it is maybe sodium, it becomes 2 to 8. So this 8, it means the outermost energy level is fully occupied, and so that is a noble gas configuration. Now, if let's say the metal atom, okay, which is, let me sodium with bonded to chlorine, okay, if we take away the whole of these other ions that are bonded to it, okay, what will be the net charge that will remain on this atom or on this ion? So that net charge that remains is what we refer to it as an oxidation state, okay? So now for group 2 elements, they have an oxidation state of +2. Why? Because they form ions by losing 2 electrons, okay? Whereas for group 1 elements, they have an oxidation state of +1. Why? Because they form ions by losing just 1 electron. So you can Okay. The elements easily lose their valence electrons to form positively charged ions, and therefore the oxidation state of group 1 and group 2 elements are +1 and +2 respectively. So it is as simple as that. So maybe if I talk about hydration energy, we can check if somebody has a... Okay? When these ions are surrounded by water molecules to form aqueous ions, first of all, they must be gaseous ions. Okay? And when these gaseous ions are surrounded by water molecules to form hydrated ions or aqueous ions, that energy that is given out, that enthalpy change that is given out, is what we refer to as hydration energy. So for those of you who had studied thermochemistry and physical chemistry, you must be aware of this, but I'm going to assume that no one had studied it before schools were closed. So therefore, what is hydration energy? It is the energy that is given out. We can say enthalpy change. Enthalpy means energy. So enthalpy change, energy change that occurs. But in this case, the energy is given out. So the reaction is exothermic. So that enthalpy change that occurs when one mole of gaseous ions, there is an S here, it must be there. Okay? If you say 1 mole of a gaseous ion, this is wrong. Okay? Sorry for that. Because a mole, if you say mole as mole, it contains 6 times a 6.0, is it 02 times 10 power 23 particles. Now if they are ions, they have Avogadro's value. If they are ions, then it means they are 6.02 times 10 power 23 ions. That's 1 mole. So if you come and say 1 mole of gaseous ion of a this one is wrong. That is not chemistry. If you want to use a gaseous ion, then don't write mole. If you want to use mole, then write mole. I remember I emphasized this when we were studying the ionization energies, electron affinities. I emphasized this, but this was just a mistyping. Oh, yeah, it was a mistake. So 1 mole of gaseous ions is completely surrounded by water molecules, okay, to form an infinitely diluted solution. Okay, you must dilute them up to infinity. The solution should not be saturated with ions. In other words, all these ions must be diluted such that water is in large excess. I don't know if you have ever heard of that term, but it is correct. Okay? So if water is in large excess, that means the solution is really diluted and all the ions have been fully surrounded by water molecules. Okay? And so that enthalpy change, that energy change which occurs, okay, is what we refer to as hydration energy. Now this hydration energy together with lattice energy, they are key, they are important, okay, as far as determining the solubility is concerned, because they might give you lattice energy and they give you hydration energy, and they say predict whether the salt is going to dissolve. Then from the two, both lattice energy and hydration energy, then you can determine. We are going to find it. Don't worry. We are going to find it. So now what are the factors which affect, okay, the magnitude of hydration energy? What are the factors which affect the amount of heat that will be evolved when gaseous ions are surrounded by water molecules? Now the magnitude depend on the ionic charge and the ionic radius, but together you can summarize them as charge, charge, density. Okay? Now, what does this mean? the higher the charge density, okay, the lower the charge density, the weaker the attraction of the water molecules, okay, hence the lower the hydration energy. Now, let me illustrate this with this. Assuming I have my crystal lattice, okay, let me use the common salt, the one that you dissolve when you are going to eat. You get your sodium chloride, okay, which is a salt, okay, and it is an ionic salt. You dissolve it in water, okay, and it is able to dissolve. And how is it going to dissolve? By dissociating into ions. But these ions, they are in aqueous solution, okay, sodium ions and chloride ions, they are in aqueous solution, but you are dissolving this as a solid. So dissolving it as a solid, therefore it must first dissociate, okay, to give you the ions in gaseous, sodium ions gaseous, okay, plus chloride ions, okay, also gaseous, chloride ions. Now the whole of this is what we call the lattice energy, okay, you can call it delta H lat. So this is the lattice energy. Now this lattice energy, this is air, not heat. This lattice energy is dependent on different factors, and they include the one you can call it atomization energy, okay. Now then, what is atomization energy? Converting this crystal lattice, okay, this one, or individual atoms, okay, you first atomize them, okay, by converting them into gaseous atoms. Or if not, you can call it sublimation energy. Now depending on what you are doing. If they are metal ions, then it is atomization energy. But for this one, you either call it sublimation energy or bond dissociation energy. Now after converting them into gaseous atoms, then they undergo ionization energy or electron affinity, okay, depending if it is a non-metal, then it will undergo electron affinity. If it is a metal, then it will undergo ionization energy to form gaseous ions. Now depending on how many outermost electrons do you have or do you want, then to determine, you can undergo first, second, third, then you can undergo first electron affinity, second, third. Then finally, after forming these metal ions in these ions in gaseous state, then these ions must be surrounded by water molecules, okay, to form aqueous ions. And this heat change is what we call hydration energy, okay, delta H hydration, this one. Now what happens? Basing on the charge density on the ions, maybe this is your sodium ion, okay, basing on the charge density of these ions, okay, and the charge density is determined by ionic radius and the ionic charge. The water molecules that will surround this ion, they will receive a high force of attraction. They will receive an attraction force. So this is water that will surround. They will receive high force of attraction. Now, as they are coming, now once these water molecules are finally attracted to this metal ion, gaseous ion, okay, and they've successfully surrounded, then that force of attraction is the one that will be given out, okay, is the one that will be given out, and it is the one that will cause change in heat or in heat energy. So now the higher the force of attraction, then the higher the magnitude of this hydration energy, okay. And what do you need to attract more water ions? you need a charge density. And so the higher the charge density, then the higher the attraction, and so the higher the hydration energy. So basically, it is as simple as that. So down the group, you can tell among these group 2 and group 1 elements, how is hydration energy going to vary down the group. So you expect hydration energy to decrease, okay, down the group. And why is it decreasing? The ionic radius is the ionic radius is increasing, but the charge remains the same. So the charge density, okay, is decreasing. And so the force of attraction for these incoming water molecules is going to be low, and so this energy is going to be evolved. Is that okay? Yes. So basically, that's how hydration energy is. And if you had to compare between the individual groups for both group 1 and group 2 elements, let me do the cleaning. You find that group 2 elements have relatively a high hydration energy compared to group 1. Why? Still dates back to the charge density. That you find out that group 2 elements have a relatively high charge density. Why? The charge is high, okay? The ionic charge is high, and the radius is small. Remember, atomic radius or ionic radius decreases across the period. So group 2 elements are relatively small in size than the group 1 elements with a high charge. So the charge density is high. So water molecules, they will be strongly attracted, okay, as they are added to these metal ions. And so that force of attraction now is going to be given out, okay, which is seen as hydration energy. Okay, that's pretty good. So before we talk about the chemical properties, which is easy, the chemical reactions that these elements do undergo. And the first one is reaction with hydrogen. Now, you remember in organic chemistry where we talked about hydride shift. So here I'm going to talk about more what a hydride is. Okay? Now, the hot metals when they are heated, when these group 2 elements and group 1 elements, when they are heated, they react with hydrogen. It must be dry. Okay? It must be dry, not moist. So they react with hydrogen gas to form the ionic hydrides. Now in this case, hydrogen reacts as a hydride. Why hydride? Because it is reacting with most electropositive elements. Imagine group 1 elements, group 2 elements. So they are highly electropositive. Okay? And so being highly electropositive, they induce this hydrogen to react as a hydride. Which hydride? By receiving. For example, you can see, yes, since metals are more electropositive, then the oxidation state of hydrogen is going to be -1. Okay? The hydrogen now receives an electron. So those are the unique properties of hydrogen. The unique properties of hydrogen. That, sorry for that, that the hydrogen can react as a proton. Now here, depending on what hydrogen is reacting with. Okay? If it is reacting with a highly electronegative atom, then it is going to react as a proton. Okay? And it loses its one electron to form a proton. But when it is reacting with a highly electropositive element, okay, then the hydrogen behaves as a hydride, where it is going to receive that one electron, okay, to form a hydride. I hope this is okay. So that's why the equation is this. So sodium plus hydrogen you form sodium hydride. Now here, organic chemistry, the magic bullet is with writing equations. And the equation must be well balanced. Not just any equation, not just, should be well balanced. And the symbols must be written clearly. Okay? That's why I was able to write these ones clearly. Okay? So the state should be superscript, no subscript, yeah, not superscript. Should be down, not as this, even this, even this. Okay? Then the elements, the letters, anyway, you know how to write chemical equations. And we mind. Actually, if you were able to listen to yesterday's speech, one of the comments, I mean, when they were releasing exams, one of the comments is that chemistry students, science students, the comment was general, that they are half-baked. Number one, you don't know how to record results. Number two, you don't know how to write equations. You write wrong chemical elements, and you also write wrong chemical equations and not balanced. That is the general comment that was given for the poor performance of science. So, please, if your handwriting is not as good, you can still start now, practice as much as you can. Okay? To perfect these chemical symbols. Don't write sodium as this. You are writing this, that this is sodium. Is it halfway? Automatically not, it's not halfway. So that one cannot be sodium. Okay? You write chlorine, and you write this. This can't be chlorine. You write sodium hydride. This is what you write. Sodium hydride. This cannot be sodium hydride. Okay? Those minor things, those things you take minor, they are the ones that are considered most. Okay? Yes, I've told you. Now the remaining part is yours. If you were to do an exam, I would cross you seriously. You write for me this, I cross. Then it should be balanced. I hope by this level, all of us know how to write a well balanced chemical equation. If you don't know how to balance, then start now. Okay? Actually, in chemistry, in organic chemistry, this is also another trick that I use. If the equation is, if I'm not sure of the equation, but I know the products, or you might not be sure of the products, I write an equation. If it fails to balance, then that equation is wrong. But don't bet on that. Don't rely on that. It is not a guarantee. Okay? Yes. So that is basically how these metals react with hydrogen. Now with water, let me erase this ink. Now with water, all group 1 elements react readily with cold water to form strong alkaline solutions. Why? Because group 1 elements are highly electropositive. Okay? They are highly electropositive compared to group 2 elements. For example, sodium or potassium, it will react with water to form potassium hydroxide, okay? And the hydrogen is going to be given off as a gas. So this is general for all. And the more you go down the group, the more the reactivity increases. Why? Because the more you go down the group, the more they become electropositive. So the higher the electropositivity, the higher the ease to lose their outermost electrons. Now, with water, however, the chemistry is with group 2 elements. Okay? The chemistry is with group 2 elements, where all group 2 elements sorry, except beryllium, okay, react with water to form. Now it depends. If it is steam, anyway, we shall see there is magnesium also, it tries to. So they all react with water except beryllium to form, to liberate hydrogen gas and an alkaline solution, depending on a metal that is reacting. Okay? And the reactivity, of course, increases down the group. That's why you are forming this alkaline gas. Why? Because the electropositivity still increases down the group. I talked about this. Now, however, with beryllium, okay, this one, it does not react with water in any form. Whether water is in gaseous state, whether it's water vapor, whether it is water to liquid water, this beryllium does not react with water. Take note. This is the chemistry. I'll set a question, discuss how group 2 elements react with water. You must be able to know this science. That keep in mind that beryllium does not react with water. Then magnesium, for it reacts with water, but only in vapor phase. Okay? It must be water vapor. And when magnesium reacts with water vapor, then you form an oxide. In this case, not a hydroxide. Okay? You form an oxide, and then hydrogen gas is given off. Okay? Is liberated. So now these two, they are the ones that have Ruzungu. They are the ones that have more English. But now the rest of the members, calcium, cesium, barium, sorry, strontium, not cesium. Cesium is in group 1. Calcium, strontium, barium. Now these ones, they react readily with water, whether in steam, whether in gaseous, sorry, in liquid state, to form their hydroxides and hydrogen gas. Is that okay? Let me repeat. Beryllium does not react with water. You can make a summary. Beryllium does not react with water in any form. But magnesium reacts with only steam. Okay? But with cold water, okay, it might react, but the reaction is slow. But it's vigorous with steam to form an oxide. Okay? And the equation is there. And hydrogen gas. But now the rest of the members, they react readily with water to form their hydroxides, their metal hydroxides plus hydrogen gas. So it is as simple as that. Okay? And so that is the equation. M reacts with water to form hydroxide and hydrogen gas, where this M can be calcium, barium, or strontium. Okay? So in case anybody has a question, and let me check, somebody might have. Now remember, they are metals, so they are highly electropositive. So you expect them to react vigorously with acids to form salt, and hydrogen gas is given off as a gas. So group 1 elements, they react vigorously or violently with dilute acids to produce a salt and hydrogen gas. So it is as simple as that. You can write a general equation, okay, where M, this is a metal atom. It can be group 1 or group 2, reacts with your gas to form a metal salt, okay, and hydrogen gas. Now those are group 1 elements. Now with group 2 elements, They do react, however some. Now the you should note, anyway, we shall find it down. You should note that in group 1 elements, their chemistry is not that complicated. But now with group 2 elements, okay, they have beryllium and they have magnesium, okay, that try to complicate things. Why? Because of the differences in charge density, okay, as we are going to explain. So group 2 elements react, but the reaction becomes more vigorous as you go down the group, except with dilute sulfuric acid. Now you should be thinking about why sulfuric acid. Why sulfuric acid? And the chemistry is simple. Now as you go down the group, the solubility of the metal sulfate, okay, metal sulfate that is formed the solubility decreases down the group. That barium sulfate, it is an insoluble salt. Calcium sulfate, but magnesium sulfate, yes, it is pairingly soluble. So meaning, as you go down the group, the reaction would be that vigorous, but because you are depositing this insoluble salt, then you won't see that, you won't be able to notice how vigorous a reaction is. So the general equation is this: magnesium reacting with an acid, okay, to form a magnesium, depending on the acid. If it is sulfuric acid, then you form magnesium sulfate. If it is HCl, then you form magnesium chloride, and then you evolve hydrogen gas. Is that okay? Now calcium, strontium, and barium react slowly with dilute sulfuric acid due to the formation of a sparingly soluble salt that prevents further reaction. So it is as simple as that. Okay? And that is your equation. Then magnesium, calcium, and barium react with very cold nitric acid to liberate hydrogen gas, which is you form a nitrate and hydrogen gas, which is almost the same. Now, why isn't beryllium appearing anywhere? Think about that. What's up with the chemistry of beryllium? Okay? Yes. Now this will take us back to diagonal relationship. We see that beryllium, for it now, it resembles aluminium. Why? Because of the reasons we talked about and the reasons we are going to see. Now, how about with oxygen? Here, group 2 elements, they do form normal oxides. And what is a normal oxide? These are the oxides. If you react maybe your metal atom, maybe N, and this is in group 2, okay? You react it with oxygen, and also this one, it has a valence of 2. If they exchange, then they are going to form, okay, N, sorry, not 2, then, and this one is going to be our normal oxide. That if you dissolve this oxide in water, then you're going to form a basic solution. Okay? Now those are with group 2. So that is generally an equation, our M reacting with oxygen as a gas to form our metal oxide. Somebody has something to say? Or somebody has joined? Somebody has something to say? Or it was some network connection? Okay, so they form normal oxides. But now, with barium and strontium, okay, they have that ability of forming peroxide when they react with, when the normal oxide is heated with more oxygen. They have that ability of forming a peroxide. What is a peroxide? So if you get the barium, and I have the equation here. So if you get the barium oxide and you heat it with more oxygen, you can form a barium oxide. Now, the normal oxide of barium, it is just BaO, where this barium is in +2 oxidation state. But you see, this is a peroxide. And the reason is simple. I remember I've explained this, but we shall talk about it more. Now, with group 1 elements, their reaction with oxygen varies, okay, basing on where you are. If you are in period 2, then period 3, then period 4 downwards, okay, the reaction varies. That in period 1, that is lithium, so for it will form a normal oxide. In other words, you react lithium, okay, with oxygen, you form, so you must put states. So this is a solid. You must put states. So we shall form our lithium, okay, and then there is a 2 here, oxide. This is a solid, okay. So this one is a normal oxide. I won't pick, I'll call them after. Now this one is a normal oxide, okay. Now, how about sodium? Now for it, sodium, it misbehaves. That, let me do the cleaning so that you can see. Now with sodium, for it forms a peroxide, okay. That when you react sodium, okay, sodium with oxygen, there is S here, with oxygen, we shall form a peroxide. There is gas, this is a gas, then we shall form a peroxide, which is sodium. So if you do this, we shall cross you. So this is sodium, then there is a 2 here, then oxide with another 2 here, and this is a solid. So this is a peroxide. And if we dissolve this oxide in water, for instance, then we shall produce hydrogen peroxide, hydrogen peroxide, okay, and sodium hydroxide solution. So why all this? Why this science? Why? And actually, if you continue to go down the group, you'll be able to find that now you advance from a peroxide to a superoxide, okay. And what is a superoxide? If you have your potassium, for instance, this is a solid, okay, and you react it with excess oxygen gas. I hope, do I have an equation? How we shall form a superoxide, and that is how we write a superoxide. Now, why this? So I say you must be able to see some relationship, okay. Yeah, I have an equation, it's there. You must be able to see some relationship that with lithium, okay, you are forming a normal oxide, but with sodium you are forming a peroxide, but with potassium and below you are forming a superoxide. What is the science? And the science is simple. The lithium has a high charge density, and oxygen also has a high charge density. Actually, not charge density, but high electronegativity. Oxygen is highly an electronegative atom. So the high electronegativity of oxygen and the high charge density of lithium is cancelled. The lithium will be able to accommodate a high charge on oxygen. But as you go down the group, then the charge density decreases. Okay? That this sodium, if it combines with oxygen, it won't be able to accommodate the charge on oxygen. And so the charge will be distributed to other oxygen atoms, which is the same case here. Group 2 elements, for them, they do form normal oxides because they are high, they have a high charge density. Okay? And so having a high charge density means they will be able to accommodate the charge on oxygen. But as you go down the group, this barium, it will have relatively low charge density. That's why when you hit its oxide with excess oxygen, you can end up forming a peroxide. So the same applies to this. As you continue to go down the group, okay, then the charge density decreases further. That now this charge it will be able to be distributed to form superoxides. Okay, so basically that's how group 1 elements and group 2 elements react with oxygen. Is that okay? Yes. So
Teacher,
yes, and almost I've talked about the properties. Now all oxides formed are basic. Now all oxides formed by group 2 elements, okay, they are basic. Now what does basic mean? If I take you back to senior 2, you see that basic oxides, they are those oxides that react with water. Okay, there is water here. They react with water to give us the basic solutions, X then OH. Okay, so now if you get this, if you can form this basic solution, then you are a basic oxide. But now for beryllium, like as usual, this beryllium is our common culprit. It will always misbehave. For it forms an amphoteric oxide. And you remember what amphoteric oxides are? Yes. Now those are oxides that react with both acids and bases. Now basic oxides cannot react with bases. And acidic oxides cannot react with acids. But now these oxides that do react with both acids and bases, then refer to them as basic oxides. And you remember, you can beryllium, you remember the other equation? Beryllium oxide, this is a solid, okay? They reacts with, for instance, if it is reacting with an acid, maybe HCl, it will form what? You must write the states. I wanted to ignore, but it's not good. Let me be exemplary. You form beryllium chloride, which is a salt, okay? But for the symbols, you forgive me. This is aqueous, and then plus water. Now because liquid. Now because it is reacting with an acid to form a salt and water, but at the same time the same oxide can react with a base. Okay? Solid can react with a base, maybe OH. It could be sodium hydroxide. Okay? It could be sodium hydroxide. There is minus here. If you are to balance, we just put a 2 here to be balanced. And then what do we form? I think we need to add water here, plus water. The water is just for balancing the equation. Plus water, we shall get our beryllium, B, then OH. Okay? Oh, the 4 is outside. So it is as simple as that. And you have, is it 2 minus? If this is a 4, yeah, you have 2 minus, 2 plus. It is, okay, let's calculate the oxidation state. This one will be 2 plus negative 4. So if it goes this side, it becomes a plus. So this is 2 minus. Okay, so this is 2 minus. So it is as simple as this. So now, because it is reacting with both an acid and a base, okay, then we call it an amphoteric oxide. But the rest of the group members, their oxides do not react. They dissolve in water to form basic solution. So being basic, you can't expect them to react with a base, but they can react with an acid, and the reaction is the same. Okay? Yes. The peroxides that form, the peroxides that are formed by group 1 members. Okay, let me first erase this. The peroxides that are formed by group 1 members and the epoxides, they form hydroxides and hydrogen peroxide when you dissolve them in water. For example, you can have your sodium peroxide, your sodium peroxide, and you dissolve it in water, plus water. You forgive me the symbols, but I'm writing with a keyboard with a, it is not easy. You form sodium hydroxide, you form a hydroxide. Oh my god, this is too much. Aqueous plus, if you form an aqueous and then you form a hydrogen peroxide, okay, and then this is an aqueous. So it is as simple as this. Then the superoxides, for them they do form hydrogen peroxide, okay, on top of this, and then under peroxide they do liberate an oxygen atom. Okay, so for example, we can write an equation. Let's say potassium. Now your equation must be balanced. If you cannot write a well balanced equation, this is a solid. Okay, so this is potassium superoxide solid, plus water, we shall form, this is a liquid, we shall form what? We shall form our potassium hydroxide. Now writing such symbols, you see different levels. If you write such in a paper, we shall cross you. This is aqueous, okay, plus hydrogen peroxide, hydrogen peroxide, this is aqueous, then plus oxygen gas. Okay, now that is the equation. Now the next thing is it balanced? Okay, let's balance it together. Let's balance this. So what should we start with? Let's start with oxygens. So this side you have 2, then 4, then 5. This side we have 2, plus 3. So if we put a 2 here, okay, and then a 2 here, and then we put a 2 here, isn't our equation balanced? Yes, it is. It is now balanced. If you check potassium, it is okay. If you check hydrogen, you have 4, and here you have 2 plus 2, which is 4. And our equation, so you must be in position, write an equation, and the equation must be balanced. Now, such an equation, if it is marked in inorganic chemistry, you have half a mark for stating an equation, just writing an equation and writing correct symbols, giving the correct products and stuffs like that. You have half a mark. Then you have another half a mark for writing states correctly. For example, this one is an aqueous, but if you put liquid, then you don't get that half a mark. Then you also have another half a mark for balancing an equation. So basically, it is as simple as that. Okay? Yes. Any question for us? Okay, seems no question as yet. So here we have some revision questions. We can revise them together. Chlorides. And today I want to finish early. I don't want, today is a weekend. Yesterday was a Friday, today is a weekend. I want to finish early. So that you can prepare. Watch your match and enjoy. Actually, you people have sacrificed a lot. There is a match and you've attended. That shows commitment, which is good. And you'll be rewarded. So, let's see how chlorine, now the chlorides of these elements, okay? Now these hot metals, they do react with chlorine gas, okay? When heated, obviously you have to first heat it. And it will combine with chlorine gas directly to form a chloride, which is a salt, okay? And the chloride formed is ionic in nature, except with beryllium. And I think at this level you can answer why beryllium, why, okay? At this level you should answer why beryllium. And anhydrous means does not have any water molecules. Anhydrous chlorides are ionic except beryllium, which is covalent in nature. And anyway, let's talk about it. Why beryllium? It is simple. It behaves differently because it has a small atomic radius and so a very high charge density compared to other members in that group. Okay? And so if it has a high charge density, then how about its polarizing power? It is going to be so high. Okay? The polarizing power is so high that if you react the beryllium, okay, with a halogen, maybe, okay, let me represent it as X. This beryllium is going to be, if you compare the electronegativity of this halogen and the polarizing power of this beryllium, okay, the polarizing power is going to be so high that it will end up polarizing the ionic bond, okay, to become more of a covalent bond, okay, and as a result the beryllium chloride will end up becoming covalent. And even when you are comparing the reactions, okay, of chlorides of group 2 elements, you'll be able to see that beryllium chloride, for it is on its own. It is in its world, okay? So basically, that's how we read inorganic. You study a given group and then you isolate the elements that behave differently from others. And then after isolating those members, okay, and then you generalize, you write general reactions, general equations, and then from general equations, you give those exceptions. So now, all members, both group 1 and group 2, they form ionic halides, ionic chlorides, ionic bromides, ionic. They are ionic in nature. Why? Because the polarization power is not that high to polarize the ionic bond. But now with beryllium, okay, it will polarize the bond so that the ionic bond or the beryllium chloride will end up becoming covalent. So as a result, as other members have a high melting point, okay, for this one, it will have very low melting point. It will actually subnine. As other members are dissolving readily, okay, in polar solvents such as water, okay, now this one, for it won't be easily dissolved. So in other words, as other members conduct electricity, because ionic and I'm talking about the characteristics, properties of ionic compounds, this one, it will be in its own world. So it is basically as simple as that, and that's where we are going to end